Hello everybody, the next topic, related rates. Related rates are very special type of word problems. And these word problems, they describe the following situation. There are two quantities related to each other and both of them changing with time. And each of them is changing at a certain rate. And the rate of one quantity is given, and the other quantity, the rate of the other quantity, the rate of change of the other quantity is to be determined. So this is the idea. Once again, there are two quantities. Related to each other. And both dependent on time, both changing with time. And they change with time at certain rates. And the idea is that since those quantities are related to each other, their rates of change also relate to each other. Rates of change also related. And that's why this is called related rates. And among these two rates, one rate is given and the other rate is to be determined. So these two quantities are changing with time, so actually they both can be expressed as functions of time. And if they are expressed that way, so their rates of change are derivatives of those functions. So altogether we have actually four quantities around. Those two quantities, the two original quantities, each of them is a function of time, and then their derivatives, which are also functions of time. So four quantities total, two quantities, original quantities, and their derivatives, also quantities. And out of those derivatives, one rate or derivative is given, and the other rate is to be determined. Now this idea or description may be very unclear, but let me show you some examples. So this first example will be about inflating ball. So here is the description. There is a certain ball, let's say made of rubber or some elastic material. And this ball is filled with some liquid. For physical reasons, I want to assume that it is filled with liquid and not with gas. And now there is some pipe connected to this ball, and this pipe is also connected to some pump. And this pump is pumping more liquid, let's say water or something, inside this ball. Then what happens? The ball is expanding, so since more liquid is getting inside the ball, so the ball becomes larger, it is expanding. so it becomes larger. Let's assume that it's not bursting, just becoming a little larger. And so here's what's given. Given that the water is pumped inside the ball, the water or liquid is pumped at a rate of 5 cubic feet per minute. Typically, when you have a pump, then it's just written on the pump how it works, like how much of the liquid it can pump in. So it's given 5 cubic feet per minute. And the question is now, how fast does the radius of this ball increase? Because the ball is inflating, therefore the radius is increasing. So how fast does the radius of the ball increase at the moment when the radius equals 10 feet. So this is a pretty large ball, so the radius is 10 feet, and it is even increasing more. So since it is increasing because of extra liquid or extra water being pumped in, so actually it was only one single moment when the radius was exactly 10 feet. Before that it was a little smaller, and after that it will be a little bigger because it's growing all the time. And the question is exactly how fast that it grows, how fast the radius of the ball grows at that very moment when the radius equals 10 feet. Now questions like this actually are pretty important in engineering, in physics, because if the radius of the ball increases too fast, it can burst. If it's increasing slowly, then hopefully it will not burst. So let's calculate how fast the radius is increasing. Now this problem actually represents the entire idea of calculus and how calculus is different from algebra. So the idea of calculus is dynamics. Now you can see that there is dynamics going on. Like the pump is pumping water inside the ball. The ball is increasing, becoming bigger and bigger, and after more water gets in, so it becomes even bigger. So that's dynamic going on. And this is opposite from algebra. In algebra, typically they consider situations static situations where nothing is moving, and here it is moving. So it's moving, changing. So in calculus they often consider situations when things are changing, things are moving, increasing, decreasing, whatever. Now, in order to solve it using calculus, we need to follow certain procedure. This procedure is pretty long, and I want to divide it into steps, like this. So the first step, in fact, it applies to any word problem. The first step in solving a word problem is to determine exactly what this problem is asking us to find. And typically, this is expressed in the last sentence. How fast the radius of the ball increases. But since this problem is, it belongs to this type of problems, related rates. And related rates, I explained, is about two quantities. So first thing I want to do is to determine the two quantities that this problem is talking about. So I will erase the picture for a moment. So like I said, the procedure is pretty long, and I want to divide it into steps. So step 1, determine the two quantities. These two quantities should be such that they, first of all, they are related to each other, and second of all, one of them, they both changing with time, and for one of the quantities the rate of change is given, and for the other quantity the rate of change is not known, is asked for. In fact, it's easier to determine the quantity whose rate of change is asked for. So let's say part A. The quantity whose rate of change is unknown. And typically this quantity is mentioned in the question, which is the last sentence. How fast means the unknown rate. How fast something changes, that means we're asking what is the rate at which that changes. Now how fast applies to radius. So to answer this, to find this quantity, we need to look at this question, at the last sentence of the problem, and answer the following question. How fast what? How fast what? Like these two words, how fast, apply to what quantity? And they definitely apply to radius, so that's why it's radius. So the quantity whose rate of change is unknown and specifically asked for is the radius. So typically radius is denoted by r, and since it changes with time, that means it can be thought of as function of time. Like instead of r, we can think of r of t, function of time. And now the rate of this function, which is same as the derivative, so rate of change is the derivative, which is r prime or r prime of t, and this is unknown, because that's precisely what the question is asking about. Now there should be the other quantity whose rate of change is known or given. And now this quantity may not be explicitly mentioned in the problem, but there is a certain rate mentioned, which is 5 cubic feet per minute. Now what is this rate? What exactly changes at this rate? And the answer is it's the volume inside the ball. So the answer is volume. Volume. So volume is typically denoted by capital V. Again, since it is changing with time, it's increasing with time, so we can also think of it as function of time, like this capital V of t. And now the rate of it, rate of change of volume, like rate of change of anything, is the derivative. So it will be derivative of this function, like can be denoted v prime or v prime of t. And this one is known. And exactly why is it known? Because we know that liquid is pumped inside the ball at this rate. And it stays inside the ball, and that means that the volume of the ball increases exactly at that same rate. So this is rate of increase or rate of change of the volume, 5 feet cube per minute. Now here I want to explain why I want it to be liquid and not gas. In fact, many problems in calculus books involve gas, so they involve the same ball, but they talk about pumping gas. In fact, with gas it doesn't work that way, and here is why. Because when you pump gas inside the ball, then the volume of the ball will not increase by the volume of the gas that you pump in. In fact, gas does not have specific volume. It depends on pressure. Like if the pressure increases, then the volume decreases, and there is a special law in physics about that. For example, if you pump your tire in your own car and then you pump in a lot of air in it, then the volume of the tire itself will increase just a little bit. It will not increase by the amount of air that you pump in. The pressure will increase, but the volume will increase just a little bit. It's not so with liquid. When we pump in liquid, then even the pressure increases, but the volume of the liquid cannot be pressurized. So that's the difference between liquid and gas. Liquid cannot be pressurized. Liquid will stay the same volume. And therefore, whatever volume of liquid you push in with the help of that pump, exactly by that amount, the total volume will increase exactly by that amount. So because liquid cannot be pressurized. So we assume that it's liquid, not a gas. And so, like I said, rate of change of the volume of that increasing ball will be exactly equal to the rate at which the additional liquid is pumped in. So these are the two quantities: radius of the ball and the volume of the ball. So that was step one, to determine these two quantities. Now step two, these two quantities are supposed to be related, and so we need to determine the relation. Between the two quantities that we have already found, in this case between the radius and the volume. Between the quantities. Now it's supposed to be a formula, an equation. So relation, in this context, relation means equation. So it's supposed to be an equation connecting volume to radius. And this equation may actually be given in the problem. It is often given in the problem. And if it's given, then you just take it from there. But if it's not given, then okay, let's recall it. So what is this about? It's about volume of a ball. And so volume of a ball. Well, the formula for volume of a ball is V equals 4/3